180 volt amps per receptacle rule primarily applies to residential environments, not industrial settings. This rule dictates that a circuit with multiple 15 amp receptacles cannot exceed a continuous load of 180 volt amps. This limitation restricts the number of receptacles to 13 on a 20 amp circuit. In contrast, industrial environments adhere to different guidelines outlined in the National Electrical Code for branch circuit sizing. Load calculations in industrial settings are based on the actual loads connected to the circuit. Therefore, to determine the appropriate circuit breaker size for a circuit with multiple 20 amp receptacles in an industrial environment is crucial to calculate the total connected load. The process involves firstly summing the amperage rating of all connected loads. Secondly, multiply the resulting amperage by 125% to account for dereting. Thirdly, select a circuit breaker with an amperage rating equal to or greater than the calculated value. For example, consider a circuit with 5 connected loads, each rated at 10 amps. The total current is 5 multiplied by 10 amps, which equals 50 amps. The derated current is 50 amps multiplied by 1.25, resulting in 62.5 amps. In this scenario, a 60 amp circuit breaker, or higher, would be suitable. In residential environments, a 20 amp circuit breaker can be used with multiple 15 amp receptacles, provided the following conditions are met. 1. The receptacles are all on the same circuit. 2. The total load in the circuit does not exceed 180 volt amps. And 3. The circuit is protected by a ground fault circuit interrupter or an arc fault circuit interrupter. To elaborate further on calculating branch circuit loads in industrial settings, it's essential to understand the concepts of continuous and non-continuous loads. A continuous load is defined as a load that operates for 3 hours or more at a time. According to the NEC, branch circuits supplying continuous loads must be rated at 125% of the continuous load plus 100% of the non-continuous load. This ensures that the circuit breaker is adequately sized to handle the sustained current draw without tripping unnecessarily. When dealing with motors, the NEC provides specific guidelines for calculating the branch circuit conductor and overcurrent protection sizes. For single motor applications, the branch circuit conductors must have an ampacity of not less than 125% of the motor's full load current rating. The motor's full load current can be found on the motor's nameplate or in NEC tables. The overcurrent protection device, such as the circuit breaker or fuses, must be sized according to NEC 430, which provides detailed information on the maximum allowable overcurrent protection for different types of motors. For multiple motor applications, the branch circuit conductors must have an ampacity of not less than 125% of the full load current rating of the largest motor in the group, plus the sum of the full load current ratings of all other motors in the group. The overcurrent protection device must be sized to protect the branch circuit conductors and each individual motor. NEC 430 provides detailed guidance on sizing overcurrent protection for multiple motor applications. In addition to considering the load calculations, it's also crucial to take into account voltage drop when sizing branch circuit conductors. Voltage drop occurs when the voltage at the load end of the circuit is lower than the voltage at the source end due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction, reduce efficiency, and even damage equipment. The NEC recommends limiting voltage drop on branch circuits to 3% for power, heating, and lighting loads, and 5% for feeder circuits. To minimize voltage drop, it's important to select conductors with an appropriate size and material. Larger conductors have lower impedance, which reduces voltage drop. Copper conductors also have lower impedance than aluminum conductors for the same size. In industrial environments, it's common to use metal conduit for branch circuit wiring. Metal conduit provides excellent physical protection for the conductors and also serves as an equipment grounding conductor. The NEC requires that metal conduit systems be properly grounded to ensure electrical safety. Grounding helps to prevent electric shock hazards and also provides a path for fault current to flow back to the source, which allows the overcurrent protection device to trip and clear the fault. When installing receptacles in industrial environments, it's important to select receptacles that are rated for the appropriate voltage and amperage. Receptacles must also be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or Intertek. In areas where moisture or corrosive substances are present, it's important to use receptacles that are specifically designed for those environments. These receptacles typically have corrosion-resistant materials and watertight seals to protect the electrical connections. Ground fault circuit interrupters are required in certain locations in industrial environments, such as wet locations and areas where personnel are likely to come into contact with water. A ground fault circuit interrupter is a device that detects small amounts of current leakage to ground and interrupts the circuit to prevent electric shock. Arc fault circuit interrupters are designed to protect against fires caused by arcing faults in electrical wiring. An arcing fault is a dangerous condition that can occur when electricity jumps between two conductors, creating heat and potentially igniting nearby combustible materials. Arc fault circuit interrupters can detect these arcing faults and interrupt the circuit to prevent a fire. The NEC requires arc fault circuit interrupter protection in certain locations in residential environments, such as bedrooms. While not typically required in industrial environments, a side protection can still provide an added layer of safety. When working with electrical systems in industrial environments, it's essential to follow all applicable safety regulations and procedures. Qualified electrical workers must be trained and experienced in electrical work and must use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Lockout/tagout procedures must be followed to de-energize equipment before performing any maintenance or repairs. Regular inspections and testing of electrical systems are crucial to identify and correct any potential hazards. Thermographic surveys can be used to detect hotspots in electrical equipment, which can indicate loose connections or overloaded circuits. Insulation resistance testing can be used to assess the condition of insulation on conductors and equipment. In addition to adhering to the NEC, it's also important to comply with any local electrical codes and regulations. Local codes may have additional requirements that are not covered in the NEC. Consulting with a qualified electrical engineer or inspector can help ensure that electrical systems are designed and installed in accordance with all applicable codes and regulations. When upgrading or modifying existing electrical systems, it's important to assess the capacity of the existing service and distribution equipment. The existing service may not be able to handle the additional load of the new equipment, which could require an upgrade to the service entrance conductors, service disconnect, and distribution panel. It's also important to ensure that the existing grounding system is adequate to handle the increased fault current. In summary, sizing circuit breakers for industrial receptacle circuits requires careful consideration of the connected loads, the NEC guidelines, and voltage drop. By following the proper procedures and adhering to safety regulations, you can ensure that electrical systems are safe, reliable, and efficient. Remember to calculate the total connected load, accounting for continuous and non-continuous loads. Multiply the continuous load by 125%. Select a circuit breaker with an amperage rating equal to or greater than the calculated value. Consider voltage drop and use appropriately sized conductors. Utilize metal conduit for physical protection and grounding. Install appropriate receptacles rated for the environment. Use ground fault circuit interrupters and arc fault circuit interrupters where required or recommended. Follow all applicable safety regulations and procedures. Consult with a qualified electrical engineer or inspector when necessary. Remember that a 20 amp circuit breaker can be used with multiple 15 amp receptacles in residential settings if the total load does not exceed 180 volt amps and the circuit is protected by a GSCI or SI. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical installations in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. The NEC is not a law itself, but it is widely adopted by state and local governments as the basis for their electrical codes. Compliance with the NEC is essential for ensuring the safety of electrical systems and preventing electrical hazards. The NEC is divided into chapters, articles, and sections, each covering a specific aspect of electrical installations. Chapter 1 covers general requirements such as scope, definitions, and wiring methods. Chapter 2 covers wiring and protection, including overcurrent protection, grounding, and surge protection. Chapter 3 covers wiring methods and materials, including conductors, cables, raceways, and boxes. Chapter 4 covers equipment for general use, including appliances, lighting, and motors. Chapter 5 covers special occupancies, such as hazardous locations, healthcare facilities, and recreational vehicles. Chapter 6 covers special equipment, such as electric signs, electric welders, and electric vehicles. Chapter 7 covers special conditions, such as emergency systems, standby power systems, and fire alarm systems. Chapter 8 covers communications systems such as telephone, data, and cable television. Chapter 9 contains tables and examples for calculating electrical loads and sizing conductors and overcurrent protection devices. The NEC also includes informative annexes that provide additional guidance and information on various topics. The NEC is a complex and comprehensive document, and it is essential for electrical professionals to have a thorough understanding of its requirements. Regular training and continuing education are crucial for staying up to date on the latest changes and revisions to the NEC. In addition to the NEC, there are also other standards and guidelines that may apply to electrical installations, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. These standards cover a wide range of topics, including power quality, grounding, and electrical safety. It's important to be familiar with these standards and to comply with them where applicable. Electrical safety is paramount, and it's crucial to take all necessary precautions to prevent electrical hazards. Always de-energize equipment before performing any maintenance or repairs. Use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Follow lockout/tag-up procedures to ensure that the equipment cannot be accidentally energized while work is being performed. Regular inspections and testing of electrical systems are essential for identifying and correcting any potential hazards. If you are not qualified to perform electrical work, it's important to hire a licensed and experienced electrical contractor. Attempting to perform electrical work without the proper training and experience can be dangerous and can lead to serious injury or even death. In addition to safety, it's also important to consider energy efficiency when designing and installing electrical systems. Using energy-efficient lighting, appliances, and equipment can save money on energy bills and reduce the environmental impact of electrical consumption. Installing occupancy sensors and timers can also help to reduce energy waste by automatically turning off lights and equipment when they are not in use. Power quality is another important consideration for electrical systems. Poor power quality can cause equipment to malfunction, reduce efficiency, and even damage equipment. Power quality problems can be caused by a variety of factors such as harmonic distortion, voltage sags, and voltage swells. Installing power quality monitoring equipment can help to identify and diagnose power quality problems. Implementing power quality solutions such as harmonic filters and voltage regulators can help to improve power quality and protect electrical equipment. The NEC provides specific requirements for grounding and bonding of electrical systems. Grounding is the intentional connection of a neutral conductor or equipment enclosure to earth. Bonding is the connection of metal parts of an electrical system to form a continuous electrical path. Grounding and bonding are essential for electrical safety and for providing a path for fault current to flow back to the source, which allows the overcurrent protection device to trip and clear the fault. The NEC requires that all metal enclosures and equipment be properly grounded and bonded. The grounding electrode system must be properly installed and maintained. Surge protection is another important consideration for electrical systems. Surges are transient overvoltage events that can damage electrical equipment. Surges can be caused by lightning strikes, utility switching, and other events. Installing surge protective devices, or SPDs, can help to protect electrical equipment from surges. SPDs are designed to divert surge current to ground, preventing it from damaging sensitive electronic components. The NEC requires surge protection in certain locations, such as service entrances and critical equipment. Regular testing and maintenance of SPD are essential to ensure that they are functioning properly. In conclusion, electrical systems are complex and require careful planning, design, and installation. By following the NEC, adhering to safety regulations, and considering energy efficiency and power quality, you can ensure that electrical systems are safe, reliable, and efficient. Remember to hire qualified electrical professionals for any electrical work and to stay up to date on the latest changes and revisions to the NEC and other applicable standards.